All right, mathletes, we are going to finish up our 10.4 notes here. In our last video, we did the problem about Michael shooting his free throws. He was going to shoot 20 free throws, and he shot with a 90% accuracy. And we did some binomial probabilities. We did a couple of pieces of this example, I think A, B, and C. What I don't have written on these notes here, I just kind of grabbed a different key before I left school, but what I don't have here is the formula. So kind of a good start to this video is to remind ourselves of this formula here. In order to find the probability of you having k successes in n trials of some random variable x is n choose k, and you can use that other notation with the n over the k. N choose k, and then we're going to multiply that by the probability of success, which we call p, taken to how many successes you have. Well, what we're saying is we're going to have k successes, so that's going to be taken to the k. And then we'll multiply that to the probability of failing, which is 1 minus p, and then we'll take that to the number of times that we're going to fail. Well, out of n trials, if we succeed k times, that means that we fail the other times, which would be n minus k. So that's the formula that we've been using. We also talked about how to use our graphing calculators in order to use what's called binom PDF, or we briefly got into binom CDF, and we'll talk about that a little bit more as we go through this example and the next example. So on these notes here, I have something that I don't think is a bad idea for you guys to put down too. It's just a reminder of checking whether something is binomial. It can be represented using a binomial distribution or not. So in other words, we need to check these things. Are there two outcomes? Yes. Michael's either going to make or he's going to miss his free throw. Are these independent trials? We're going to assume that they are. There's a lot of psyche that goes into shooting free throws, but we're just going to say that he is shooting each free throw with 90% accuracy. All right, obviously things go into that too, but as mathematicians, we like to make things simple. So the next thing we want to check is the probability of success the same for each trial? Does that remain the same? Yeah, we just said he's going to shoot with a probability of 90% accuracy each time. 10% chance he's going to miss. Okay, in the last video, we did these problems here. The probability of him making all 20. This is a little bit neater, I think, than what I had on the smartboard. On the smartboard, in the last video, we just calculated it by doing this. And I kind of mentioned how we could do this, and these are really going to be one. I talked about how it wasn't necessary. So on the smartboard lesson, we just did 0.9 to the 20th, which I think falls in line with other probability problems that we've done before. So the probability of him making 20 free throws, we said, was 0.12158. And then we did exactly 18. So now we need to do the 20 choose 18. How many different ways can he make 18 free throws out of 20? And then what's the probability of him making 18 free throws and missing 2? And that's basically what that's calculating right there. And that ended up being about 28.5%. On our calculator, when we do this one here, we do the binomial PDF because it says exactly 18. So that's when you want to use the PDF and you're looking for an exact value. And then it goes NPK. If you have a newer calculator, it gives you a little template to put it in. This is how you would have to type it into an older calculator. At least 18, we talked about how we could add the two that we just calculated, 18 and 20, to 19. That's the only new one we have to calculate. And so I'm kind of wrapping up what we did in the last video here. Oh, it doesn't look like I finished this example here. We'd add those three probabilities together. We could also do this one on the calculator by doing, I'm just going to put this here. If we did this one on the calculator, we would do 1 minus at least 18 means 18, 19, or 20. So I'm going to find the probability of what I don't want. The probability that he makes less than or equal to 17. Because this is something that our calculator can do using this guy right here, this binom CDF. All right, so we could go 1 minus binom CDF, and then if we put in 20, there's n, and then p is 0.9, probability of success, and then we said he's going to make up to 17. This C means cumulative. It always means finding the probability of making 0 up to whatever number you put there. So this calculation here is finding all 18 of those probabilities, 0 through 17, all 18 probabilities, and it automatically adds them up, which is actually pretty cool. And then when we subtract that from 1, we get what we really want, which is the probability that he makes at least 18. Okay, I don't have that calculation, and I also don't have a calculator, so I'm going to have to just rely on the answer that we got in the last video. Do you want to go grab that calculator for me? Okay, my math assistant is going to go grab me my calculator here. So the next question says at least 1. Instead of doing that one, I've changed this to 10 here. Don't really know why, but it sounds like a good thing to do here. So the probability of making at least 10, okay, is going to be the complement to making 0 through 9. So since my calculator can do this, I want to use that advantage and try that CDF on my calculator again. Okay, just in case we need it. Now I got it. Thank you. Welcome. Okay, so we've got, and this is a lot of notation. You know, this is something you'd probably show in like a stats class or something. Really, all this stuff is. You know, if you just actually showed me in this class something like actually, I don't think this is a bad idea. This kind of shows you know what's going on, and then maybe write what you type in your calculator, so I can give you some partial credit if you mess this up. Maybe you put these in the wrong order or something. Although that'd probably give you an error, but probably the most common thing is a student accidentally will use the PDF here. We want to use CDF. We want to add all of them up to 9, but then subtract that from 1. Okay, the probability of making up to 9, so 0, 1, 2, all the way up to 9 is pretty small. So the probability of making at least 10 is going to actually be pretty big. And the reason is, I mean, this is almost 100%. And the reason is because he's a good free throw shooter. He makes 90% of his free throw shots, which is pretty darn good. So the probability, the thing about what this is saying, that he makes at least 10, that's a lot of different possibilities. He can make 10 or 11 or 12, all the way up to 20. So there's a pretty good chance he's going to do that since he's such a good free throw shooter. That's why I changed this, to be honest with you, because the probability of at least 1, if we calculated that out, would tell us pretty much 1. It would be 0.9 repeating for a long time. That would be almost exactly 1. All right, the probability of at most 15, same idea. Okay. Oh no, I'm sorry. This says at most, not at least. So we don't need to do the whole 1 minus thing here. We just need to use our CDF, okay, again, because it's cumulative. At most 15 means 0 through 15. That's exactly what the CDF function, the binomial CDF function is built for, is to add all the probabilities from 0 through 15. This is by definition what that CDF is used for, so we are basically just going to use that. 20 is our n value, 0.9 is again our probability of success, and then we're looking to make it up to 15 times. CDF, where is it? CDF up to 15. Okay, so I don't have that. Why don't I use this now as a chance to kind of do a CDF here. So we'll clear this out. We're going to type this in. Oh, I'm just kidding. I do have it right there, 0.0432. All right, we can move on. So a little bit more on the calculator stuff here. Binomial PDF, you type in NP. I put X here. I think that's what your calculator calls it, is X. In our notes here, we've called it K. It's the number of successes, number of trials, probability of success, and then the number of successes. Hey, Laura, if you find a pencil, could you bring it to me, please? This finds the probability of exactly that number of successes. So if, I don't have this finished here. Finds the probability of exactly X successes. Where the binomial CDF, which is again going to be, thank you. Okay, this is going to find the probability of exactly X successes. Probability that our random variable has exactly X successes. And you can write that in words too. Finds the probability of X successes in N trials. Okay, with that probability of success. Binomial CDF, it's the same thing. It's NPX. This, though, means cumulative this time. The P up here, the PDF really stands for probability distribution function. Or, I'm sorry, I think it's actually probability density function. And it gives you the exact. This one gives you the cumulative density function. So we have NPX px, same things, but it'll go up to that value. And then this is a pretty straightforward, well, I don't know if it's straightforward, but this is a really good way of putting it. Finds the sum of the k or fewer successes, or from 0 to k. Probability of 0, 1, all the way up through k, and it adds those together. All right, and then this kind of discusses binomial probabilities in the calculator, but I think we've talked about that quite a bit, so I'm not going to go over that. You can look at that if you'd like. Let's get through the rest of these examples here, so we can get this under 15 minutes for once today. So down here it says, if you want to find the expected value for a binomial distribution, we talked about expected value in our first video for this section. We basically, talked about expected value being, and then we had this mu. Really, for this class, I'm just going to use e of x. Expected value of our random variable x is each outcome multiplied by its respective probability, and then we add those all together, and that'll give us the expected value. So the expected value when we roll a die ended up being 3.5. This loaded die that we had down here was 4.4. That was expected value, just as a reminder. So if you want to find the expected value of a binomial distribution, then we can easily find it just by taking our probability of success and multiplying it by the number of trials. I mean, step back for a second, get rid of all the probability talk that we've talked about here. And if I just said to you, hey, this kid Michael makes 90% of his free throws. He's going to shoot 20 free throws. How many do you think he's going to make? Well, you would just multiply that 90% by the 20 and say, hey, he's going to make about 18 free throws. That's your expected value. Okay, so what that means is if he were to repeat this many times, so if he were to do these 20 free throws at a time many times, we'd expect the long run average to be 18. So expected value for binomial distribution is very intuitive. It's pretty straightforward. You multiply your p by your n. I don't even know if it says that anywhere here, but we could really just write that in our notes here too. The expected value of x, if it's binomial, is just p times n, or n times p. All right, so on to our last page here. Sticking with an expected value problem here. Sorry. All right. It says a fair coin is flipped 5 times. What is the expected number of heads? Well, let's think about what that probability is. The probability of success now is 0.5. Flipping a coin, getting head, 50%. So I wrote here P, our probability of success, is the probability of getting a head, which is 0.5. We're going to have five trials, We're going to flip the coin 5 times. The expected value is n times p, 5 times 0.5. We expect to get 2.5 heads. All right, now what I also did here is I made a probability model for the number of heads when you flip it 5 times. So what I did here is I put up all the different things that could happen when it comes to getting heads when you flip a coin 5 times. I could get 0 heads, 1 head, 2 head, 3, 4, 5 heads. Those are the only things that could happen. And then I found, so the one that we just talked about, or we talked about what the expected value is. Now I'm looking at the entire probability model. These are all the things that could happen. So this is getting the probabilities. I think I only have one written here, but we'll just use one that I have written here. This is just using our binomial distribution formula. Okay, so for p equals, x equaling 2, getting 2 heads is going to be 5 choose 2. And then I'm going to take my probability of success to the number of successes, probability of failure to the number of failures. If I got 2 heads, I got 3 not heads, or obviously tails. That's where I got the 10 30 seconds from. I did that for each of these, and then I got this probability distribution. So obviously, if this is a good probability distribution or good probability model, these have to add to 1. They have to, which they do. All right. It says a chimpanzee is shown 100 questions from multiple choice tests. Basically, the fact that these are chimpanzees is just to say they're just guessing, okay? They're just going to guess at each answer on the screen, so they have no idea what they're doing. If there's 100 questions and they're just randomly guessing at things, what's the expected number of things that they would get right? Well, it's a multiple choice test that has 1, 2, 3, 4, 5 choices. That means there's a 1/5 chance of getting one question right, 4/5 chance of getting it wrong. So the expected value is just going to be those 100 questions times 1/5. We expect them to get 20 questions right just by simply guessing. Chimp is expected to get 20 questions correct just by guessing. Okay, and then we have our standard deviation here. Standard deviation, or the spread of a binomial probability distribution, is found by taking the square root of NPQ. We're not going to go into this a ton. This is more of an AP stats or a stats class sort of thing, but I do want you to see it. The standard deviation of this chimp just guessing would be the square root of 100 times 1/5 times 4/5, which is the square root of 16, which is 4, which means on average we'd expect the chimp to get 20 questions correct. But if we had, this chimp repeat this process over and over and again, he's not always going to get 20 questions correct. He might get 21, he might get 28, he might get 50. All right, but what we would expect is the standard deviation to be 4, meaning on average those values that chimp is getting correct would differ from the average, which was 20, by 4. Okay, remember the standard deviation is kind of the average that each value differs from the average. All right, so that's kind of what we would expect the spread of that chimp's number of correct to be if he did this over and over and over again. All right, so that is our last video in 10.4. Didn't keep it under 15. Maybe I'll get better at this and we'll be able to keep it under 15 for the next one. But if you have any questions, shoot me an email or make a comment in Classroom and I'll respond to it there.